Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and we'd also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Seba, and today we're digging deeper into the duration and convexity concepts that are very handy in bond valuation and risk management, and investigating why do these approximations really work and how well do they work for small and large interest rate changes and respective changes in fixed coupon bond value. So the general story is that you have got a bond with some principal, so let's say $1,000, with a coupon rate of, for example, 6% and a yield to maturity of 5%. And let's assume that it is a 5-year bond with the coupon paid annually, just for simplicity. And we can quite easily build a cash flow schedule, calculate the fair value, and then approach the concepts of duration, modified duration, convexity, and calculate, or at least approximate, what would be the impact of various interest rate changes to bond value. Because obviously, if the coupon rate stays the same, it is fixed, then increases in yield to maturity would cause the fair value of the bond to plummet, the price that you would expect to pay or receive for such a bond at the market would decrease, and vice versa. If the yield to maturity is reduced, if the required rate of return for such bond is lower, then the bond would potentially be traded at a higher premium, so its fair value and market price respectively would increase. But to model this quantitatively, duration and convexity come in handy. So let's build the cash flow schedule first and investigate these calculations. So first of all, for a bond, the outstanding debt, the principal, is not paid until the very end, the very maturity date. And for loans, for example, you could easily tweak that and compare duration profiles and interest rate risk profiles of various cash flow schedules. And by the way, that's exactly what we've done in one of the first videos on this channel, so check this out if you're interested. But here, let's just investigate a bond. Everything is generalizable to any cash flow schedule here. So in terms of our outstanding debt, at the start, it is just equal to the bond principal, and the principal is not being paid at all until the very end, where it's paid in full. Then the outstanding debt amount in the next year, or in the next time period more generally, is just the outstanding amount in the previous year minus the principal that has been paid in the previous period. And here we'll see that it remains $1,000, the principal of the bond, until the very end when it's paid in full. And the interest is charged according to the coupon rate on the outstanding debt. So here it's quite simple. We just multiply the outstanding debt by the coupon rate, locking it over here, and then we can build our total cash flow as the sum of our interest and principal payments. Again, quite logically, as with any bond, you're receiving coupons until the very end, where you receive your last coupon and the principal of the bond. Then we can calculate our discount factors for particular time periods using the yield to maturity we have specified above. The discount factor will just be equal to 1 over 1 plus the respective yield to maturity, and we can log the row here, raised to the power of the number of the year. And we can see that discount factors are getting lower and lower as time goes by, reflecting the time value of money considerations. That is quite simplistic and quite straightforward to understand. And then we can discount our cash flows using the respective discount factors, multiplying cash flows onto the discount factors we just calculated. And that would allow us to calculate the fair value of the bond, or the expected market price this bond would trade on, using just the sum of our discounted cash flows. And this will come in handy as our duration and convexity calculations would require us to divide time-weighted cash flows onto the fair value. So here it would save us quite a bit of time. Then for duration calculations, referring to this formula over here, we just calculate the time-weighted discounted cash flows and divide those by the sum of discounted cash flows, meaning that we are calculating effectively the weighted average maturity of your discounted cash flows. This is a very intuitive and understandable definition of duration. So here we can just multiply our discounted cash flows by respective points of time. By the way, if those would be not years, but for example months, you could easily generalize it using, for example, 1 month as 1/12 of the year, because as yields and coupon rates are generally quoted in annual terms, duration is also mostly quoted in years. So if you are dealing with biannual payments or quarterly payments or monthly payments, you can easily convert them into years by just dividing it by 12, for example, if it's monthly. And for convexity, the calculation is quite a bit less intuitive and less straightforward, because we have to multiply by the point in time t, and we also have to multiply by t plus 1. And then, again, dividing it by the fair value, nothing changes here from our duration concept. However, we also have to divide whatever we've got here by 1 plus yield to maturity squared. And where does this come from? Is it somehow related to the fact that to get modified duration, we divide by 1 plus yield to maturity? And it's modified duration that allows us to proxy the sensitivity of bond value to price changes. And the mathematical logic of all these calculations are related to Taylor series, surprisingly of all things, and the derivatives of the fair value of the bond by yield to maturity R. And for duration and convexity respectively, we're dealing with first derivatives and second derivatives. And that allows us to account for first order effect and second order effects of interest rate changes on bond value. So over here, if we consider the first derivative of the fair value function, which is just, again, a sum of discounted cash flows, if we are interested in how does this function respond to changes in R, we can just calculate the first derivative with respect to R, and again, as this is a sum, the derivative of a sum would be a sum of derivatives, so we can just treat those cash flows, whatever they are, separately, because it wouldn't affect the derivative calculations. And we've got our argument R only in the denominator of our discounted cash flows. The cash flows themselves, as coupon is fixed, are not affected by the changes in interest rate at all. And here we can actually see that it is a power function. We raise 1 plus R to the power of minus t, which means that the derivative of these functions would be minus t, and then the exponent of our power function would increase by 1. It would actually decrease by 1, but as it's negative, it would effectively be t plus 1 in the denominator, minus t minus 1. And here we already see something very akin to duration formula emerging just by taking the derivative of fair value with respect to R. However, as those manipulations led us to increase in the exponent in the denominator over here, we can just take 1 plus R in the front of our sum and get this 1 divided by 1 plus R that is directly equivalent to what we do in the modified duration, because to treat modified duration as sensitivity, we have to account for this 1 plus R that naturally emerges in terms of differentiation of fair value with respect to R. And obviously here we'll have the minus sign, simply because this power function is actually with negative exponent, so we can take this minus in front and keep in mind that the derivative, the sensitivity of bond value to interest rates is negative. When interest rates go up, bond value goes down, and that's why interest rates increasing or decreasing lead to fair value of bonds decreasing or increasing respectively. But then, if we consider convexity, we can take the second derivative of the same function. And here we just have to make the same manipulation twice. So we will first multiply by minus t, and then taking another derivative of that, we would need to multiply by negative t plus 1. That would make the minus signs cancel each other out. And in the denominator, we would have 1 plus r to the power of t plus 2, because, again, effectively it is minus t minus 2, but we can bring it to the denominator with the power of t plus 2. And again, just as we've done here, we can take 1 plus r squared in front of our sum, and this is exactly the convexity calculation. So convexity and duration, or modified duration more precisely, correspond to the second derivative and the first derivative of the fair value function with respect to the yield to maturity r. And here, using the Taylor series properties, that we can approximate the function using its derivatives, we have got a very natural emergence of our approximations, both first order and second order. When you take only the first term of this Taylor series-like expression, we have got this stylized fact that the change in bond fair value is equal to minus modified duration times the change in the interest rate R. And for the second order effects, we also include convexity. And here, just because it's Taylor series again, we have got our delta R, the change in interest rate, squared, and we have also got to divide by 2 factorial, which is just 2. And some of the more mathematically inclined of you might also think, why stop at second order effects? Why not calculate the third term in this expression, divide by 6, calculate the discounted cash flows weighted by t times t plus 1 times t plus 2, and it's by all means possible and it will lead to a more precise result. However, for most real-world applications, first and second order effects are more than enough, and that's what we're going to demonstrate just now. So returning to our spreadsheet calculations, we can calculate our weighted discounted cash flows for convexity by multiplying discounted cash flows by t and t plus 1, and again dragging it throughout all 5 cash flows. And finally, we can calculate our duration as just the sum of time-weighted discounted cash flows divided by the bond fair value. And we see that the duration of such a bond is 4.48 years, which is quite intuitive, as most of the discounted cash flows for the bond occur at the end, where coupon plus principal is paid out, and almost no cash flows occur earlier than that, only the coupon payments occur there, and if the coupon rate is quite low, then it is very understandable why this would be close, quite close to bond maturity for bond-like payments, and that would be much lower for loan-like payments, where parts of the principal are also paid throughout the lifetime of the instrument. And to calculate modified duration, we can just divide that by 1 plus yield to maturity here. And here we can already see that this is the origin of the first order approximation of fair value sensitivity. We can say that if yield to maturity or interest rates in general increase by 1%, the bond price would reduce by approximately 4.26%. That is where it comes from. But to account for second order effects, we can also calculate convexity by just summing these weighted discounted cash flows, dividing them by the fair value, and also dividing them by 1 plus yield to maturity squared straight away. And we can see that convexity of this bond is positive. It is equal to 23.44, and that means that linear estimations of price sensitivity would be overly pessimistic, because convexity would lead to positive second order effects that are not accounted for in the first order approximation. So now, just to keep it simple, we can estimate what is going to happen in various models and various approximations if interest rates increase by 1%. Why? Well, if interest rates increase by 1%, our yield to maturity is equal to the coupon, and it's quite intuitive that in that sense, our bond fair value should be exactly equivalent to its principal, so it would be equal to $1,000. And you can see how close to $1,000 both of our approximations get us. So for the first order approximation, we can just calculate negative interest rate change times modified duration. And again, as expected, this approximation tells us that the fair value of the bond would decrease by 4.26%. In the second order approximation, we start with the same calculation, but we also add convexity divided by 2 times the squared interest rate change. And here we see that the second order approximation tells us that the depreciation of bond value when interest rates increase would be less dramatic, but by only 11 basis points. So it means that for as large of interest rate changes as 1%, so 100 basis points, the margin of error for the first order approximation is actually quite low, only 11 basis points. However, the more terms you use, obviously the closer to the real value you get. So we can calculate those approximated fair values by just multiplying the current fair value by 1 plus the estimated price response. And we can see that compared to 1,000 that you would naturally expect, the first order approximation gives us a value of $998.80. So it's basically $1.2 away from the actual value, which is not that bad. And for the second order approximation, we can see that our approximated bond value is exactly $1,000.03. So while the first order approximation is $1.2 off, the second order approximation is only 3 cents off. It means that this is, again, much more precise of an approximation. And then we can actually use some clever Excel tricks to calculate the fair value straight away without any approximation by just summing up our cash flows that will be divided by 1 plus the original yield plus the change in such yield and raised to the power of those years. And then, as this is a matrix multiplication formula, we can actually enforce it using Shift-Control-Enter and get exactly $1,000. And this setting also allows us to see how well those two methods perform for different interest rate changes. For example, for an interest rate change as low as 10 basis points, 0.1%, the difference between the first order and the second order approximations are quite small, just 1 cent, and both are very close to the actual result. So for very small interest rate changes, the linear approximation with modified duration works remarkably well. However, if the interest rate change is more dramatic, then this discrepancy starts creeping up. And even for changes as large as 1%, the margin of error for the second order approximation is again quite small. However, if we are talking of an interest rate change as massive as 10%, which is quite improbable in the current financial environment, however still interesting to investigate and ponder, we can see that that's where the error in the second order approximation becomes material. It is actually erring in the optimistic side here, the second order approximation, because again, for first order approximation you would always get a lower value, for a second order you will always get a higher value, for the third order you would have a lower value, and then you will slowly converge to the true value when you have infinitely many terms. That's a very well-known and intuitive property of Taylor series approximations that also picks up here. And graphically we can see the property of those approximations over here in this particular chart, where we can study the approximations and the real fair value of bonds calculated directly for different values of the yield. And we can see that while the first order approximation, given us orange line over here, does a very good job for values of the yield very close to the original value of 5%, the divergence starts accumulating when interest rate changes are large, but the blue line, that is the true fair value, and the gray line, which is the second order approximation with convexity, do keep quite close together for yield changes as massive as 5%. So that is actually a very good testament to the effectiveness and to practical value of convexity in real financial applications, at least in the modern scenarios where you quite rarely see interest rate changes as drastic as 10%, for example. And that's all there is for using duration and convexity to proxy bond sensitivity to interest rate changes and the mathematical logic of why they really work. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.